It's a pleasure to be joining all of you. I'm sorry that this was scheduled on a week when I couldn't actually be up in the Berlin area to give this. I myself am a little bit tired of the Zoom environment. It has this great advantage of reaching more, accessing more speakers and reaching wider audiences. But the level of communication isn't quite the same. But we will do the best we can. Let's see. I should get the PowerPoint up and going here. Okay, so my topic today has to do with chemical habitability. That's something I will introduce briefly, but really what I'm going to be talking about is two different related themes that have to do with major volatiles in the Earth. First of all, their distribution in the present day Earth and what that might mean. And second of all, how Earth acquired its volatiles. And the real emphasis, I will be mentioning others, but the real emphasis is going to be on carbon. So the concept that myself and my coworkers and quite a number of others have really focused on in recent years is this concept of chemical habitability. I think many of us are familiar with physical habitability, that is the location in a particular solar system where a planet can have liquid water, which is a critical criterion for life being possible on any given planet, both in our solar system and in other solar systems. But even if a planet is in the physical habitable zone, there are many other criteria that determine whether or not that planet has the potential for life. And one of those criteria are that it has chemical habitability, which is, in the way I'm going to define it, the right supply of volatile elements. And the right supply means that obviously it's enough to support life, but also the right amount to support a stable climate, and then also the sufficient amount for the interior workings of the planet for some kind of tectonic stability. Now, you may notice that I'm not actually going to tell you what the right amount is, because I don't know, and I don't think we know. The thing we do know is that our planet is within the range of the right amount, but what the lower limit of the right amount might be, or the upper limit might be, we don't know. This cartoon on the lower side here is meant to illustrate that we may have a diversity of planets depending on their location or depending on other aspects of their history, from a barren rocky world to a sooty world that is completely encased in methane and organic molecules, or a water world where there's very, very thick water oceans. And our planet obviously is not in any of these extremes. It's somewhere in the chemical habitable zone. And so understanding, first of all, how our planet came to be in that chemical habitable zone is a start, not sufficient, but it's a start for defining what the limits of chemical habitability might be. And so if any of you are cosmochemists or planetary scientists, I want to make sure that I am understood when I talk about volatile elements. For the most part, during this talk, I will be talking about the major volatile elements: hydrogen, carbon, nitrogen, and sulfur, and really principally carbon. But of course, there are many other elements that have a certain amount of volatility in chemical systems, which is to say they have a tendency to evaporate. And these are known as the moderately volatile elements, for example, to people who work on meteorites. For the most part, I'm going to be talking about major volatile elements, and really principally carbon. So deep volatile cycles operate in such a way to maintain a habitable planet, and that has to do both with the surface conditions, liquid water oceans, and a stable climate and an atmosphere that has appropriate greenhouse conditions for retention of heat, and also the right supply in the interior, such that the convective vigor and the volcanic activity is, if not steady, at least regulated within a set of bounds, so that true catastrophes or true freeze up, as it were, don't occur. A number of years ago, in looking at what was known as the deep earth water cycle and the deep earth carbon cycle, which were two different aspects of my research, it occurred to me that we should compare them. There's a joke that I sometimes tell about this, which is that if a geochemist doesn't understand something, well, they're kind of stuck. But if they're in luck not to understand two things, they can make a ratio, and that is how geochemists solve problems. And so the paper that's, I guess, 14 years ago, 2009, we compared the inventories of hydrogen and carbon in Earth as compared to several other reservoirs. And two things came out of this comparison that have driven a huge amount of what I've been interested in and have worked on in the ensuing years. So this is a plot against nothing. Actually, there's nothing on the y-axis, but it's the hydrogen-carbon mass ratios of a number of important reservoirs. And the first thing that jumped out was that the hydrogen-carbon reservoir of the exosphere being all the fluid envelopes plus the crust, is significantly higher than that of Earth's interior. And so this was a surprise that required some understanding, and I'll talk some about that. In fact, that will be I don't know, maybe about the first third of today's talk will be about that. And then the second is that when one adds up the exosphere and the mantle and gets a bulk silicate Earth, that the bulk silicate Earth has a higher hydrogen-carbon ratio than the chondritic materials that you might assume would be the feedstock of the Earth. And so that is a topic, and not so much the hydrogen-carbon ratio, although that's part of it, but also just the amount of carbon and other volatiles that Earth has in its bulk silicate Earth. That's the second half of this talk. So the talk will have two different chapters, if you will. So in order to do this, there's the easy part, and that is to think about the surface reservoir. And many of us think a lot about the volatiles or other geochemical reservoirs in the interior. Turns out that just inventorying the surface reservoir gives a great deal of information about the workings, the net workings of the interior of a planet. So it's a very worthwhile exercise. The amount of water on the surface, of course, that's really just the oceans. One can take all the water in amphibole and mica and whatever in the crust and add to it, but it's just a decimal place. The water is that in the ocean. So that's a very easy number. Not quite so easy, but reasonable, is to inventory all of the carbon in sediments and sedimentary rocks on the continental shelves, in crystalline continental rocks, and so forth. And this is a summation that I did a number of years ago. All of these are the different references that I use to put this together. And we get a number, a total mass. Moving to the interior, how are we going to determine the water concentration or the carbon concentration in Earth's mantle? The way that I have gone about this is a way that follows what other people have done, but there's an important distinction, which I'll point out in just a moment. And that is to take advantage of the empirical similarity in the behavior between water and the rare earth element cerium during partial melting of the mantle. There's no particular fundamental reason why this would be, but empirically we find that water and cerium behave the same during partial melting, such that here's an example from a particular place just off the East Pacific Rise, where as the water concentration changes, the cerium concentration changes with it, such that the water-cerium ratio does not change. This has been observed many, many times for basalts, which means that if we know something about the cerium concentration of a source, we can also know something about the water concentration of the source. So this is a compilation that also from, well, I used it in 2018, but it's from fairly recently, of the whole spectrum of oceanic basalts, both from mid-ocean ridges and oceanic islands. And the amplitude of water cerium variation that they have is extremely small, just plus or minus 20%, which is a pretty good number, or a pretty good uncertainty. Now, instead of what had been done before, which is to say, okay, that gives me the water cerium ratio of various source regions, I took a different leap and said, cerium is one of a class of elements that we know a lot about in the bulk silicate Earth, which is to say that cerium is a refractory lithophile element. And the refractory lithophile elements do not volatilize, so they're not lost during volatilization. They're not segregated to the core. And because of that, they're the elements that we know the most about in terms of their concentration of the bulk silicate earth. We know their concentrations about as well as we know the concentrations of elements like magnesium, for example, and we're not going to do any better than that. So if we know the cerium concentration of the Earth's interior, and if we know the water cerium concentration, or ratio rather, then we know the water concentration of Earth's interior, except for the core, of course. I'm talking about the silicate portion of the interior. And the result of this exercise is that there is approximately 300 parts per million water in the average Earth's mantle. And for reference, 400 parts per million would be the same total mass as the Earth's surface reservoir, as the oceans. In other words, we get plus or minus about a quarter, 3/4 of an ocean in the Earth's interior. Most of Earth's water, by just a small amount, is on the surface, and a subsidiary amount, similar in magnitude, is stored in the interior. You will read many papers about water-rich regions in the interior, for example, in Earth's transition zone, which people will say is water-rich. I would argue, first of all, that just because it's water-rich doesn't mean that it has a high water cerium ratio. So therefore, the exercise is still valid. And second of all, that if it's water-rich, that we also sample it someplace in the spectrum of oceanic island basalts or mid-ocean ridge basalts. And so I'm not concerned that there might be water-rich regions. I think the exercise is valid anyway. This is a very quick slide to show you that we know almost nothing about nitrogen, but the people who've taken stabs at the amount of nitrogen in Earth's interior, and these are listed here, myself, Bernard Marchi, and Alex Halliday in the last 10 years, all get more or less the same number. That either means we know the number really well, or the constraints are so few that it's hard to get it wrong. We don't really know, but this is an interesting number too, because it's approximately the same as that of water, in that the amount of nitrogen in the interior is a little bit less than the amount of nitrogen in the surface, meaning the nitrogen in the atmosphere. They're both mostly on the surface, but not predominantly on the surface. Carbon is not like this. Carbon is really quite controversial. And so this is a compilation by publication year of estimates of the bulk mantle carbon. And you can see, first of all, that they vary by almost 2 orders of magnitude, not plus or minus 25%, 2 orders of magnitude. And second of all, that if you look by publication year, there doesn't seem to be any convergence at all, that we don't seem to be getting any better at it. I applied the same reasoning that I applied to water and cerium for carbon, but in the case of carbon, the matching refractory lithophile element is niobium, and is barium. Previously it had been suggested it's niobium, but with enough data, we now see that the barium, that the CO2 niobium ratios of undegassed or nearly undegassed basalts actually vary by quite a lot, by about a factor of 5, whereas the CO2 barium ratios vary very little. These are all the different locations that I was able to compile data for in this paper from 4 years ago, and almost all of them plot within an envelope that's about plus or minus 20%. So applying the same exercise as we did for water cerium, we arrive at a mantle carbon concentration that's shown here of about 120 parts per million. CO2 degasses very, very easily during eruption of basalts, and so one has to be careful about this. One sees a particular locality and measures the CO2 concentration in glasses or in melt inclusions or something like that. One sees that there is a high value of CO2 barium and then something going off to the right on a diagram like this, indicating increasing barium concentrations without CO2 concentrations, and that's an indication of degassing. So there's a greater risk for the CO2 barium than there is for the water cerium, because water doesn't degas nearly as easily from fresh erupted basalts. One really nice confirmation that I'd like to point to is that in Hawaii, we have 2 different ways of looking at the CO2 barium ratio. The one on the right is the conventional way. measuring the CO2 and the barium in melt inclusions. And you can see actually most of the CO2 is in this vapor bubble, but when one integrates that, one gets a ratio that looks like this. And then a very interesting study from a few years ago by Anderson in Poland, where they monitored the CO2 coming out of Kilauea, outgassing in Kilauea. And then they estimated the barium concentration being supplied to the Kilauea summit, first of all, by knowing the barium concentration of typical Kilauean basalt. And second of all, looking at the INSAR data to look at the amount of inflation to figure out how much basalt was coming into the system. And they ratioed the two. And for Kilauea, they obtained CO2 barium here, 86 plus or minus 20. Notice that this is identical from what one gets in the melt inclusions. It suggests that we're doing it, if not right, that there's some methodological confirmation of the procedure. And then also, that was 4 years ago, there's been an explosion of new data, of almost as much data published since 2018 as published beforehand. And it's beginning to show a fair amount of scatter, but if one takes the averages, one gets essentially the same value. Okay, so within that 2 order of magnitude variation, my number of about 120 parts per million carbon hopefully is a little bit better posed than some of the previous ones. Most of those, by the way, come from rare gas analyses, carbon, helium, carbon, argon, and so forth. All right, so about subequal amounts of water in the interior and on the surface, subequal amounts of nitrogen, far more carbon in the interior than there is on the surface. Most of Earth's carbon is in the bulk silicate Earth is still in the mantle, like by a factor of 4 or 5. This is a bit of a surprise. Another way to say that is, if we focus just here, if the CO2 barium ratio of the mantle is about 100, the CO2 barium ratio of the surface is far lower. Barium is an incompatible element. It comes out and gets stored in the continental crust. CO2 is an incompatible element, comes out and gets stored first in the atmosphere and the oceans, but then eventually limestones. But then somehow the CO2 barium ratio is lowered so that it is not the same as what's coming out of the mantle. And the answer to this, I think, more than likely, can only be that in a time integrated fashion, much of the carbon that has come out to the surface has been returned to the mantle by subduction. We see, oh, by the way, like this Becker et al. is Harry Becker, who I believe is with us this afternoon. We see that during subduction, barium-niobium ratio of subducted material like eclogites decreases as the barium is removed back into the continental crust by arc processes, and the niobium travels with the subducting crust. And the carbon must travel with the niobium such that the carbon and niobium are separated from one another. Without actually ever looking at an arc volcano, we come to the conclusion that carbon must be, or for that matter, at a subduction zone, we come to the conclusion that carbon must be very effectively returned to the mantle. Okay. Chapter 2, a very different sort of perspective on that other question. And the other question is Earth's carbon and how it gained the amount that it did as compared to its supply during its accretion. And this older diagram that I started at is just hydrogen carbon. Later on, people, including myself, but others as well, looked at the whole gamut of elements, carbon, hydrogen. I don't know how neon got lost over there. It belongs over here. Carbon, hydrogen, nitrogen, rare gases, sulfur, and so on. And we see that these gases, or that these volatiles, are fractionated relative to one another, which means that there are interesting processes going on during either the delivery or the retention of these volatiles in the early differentiation of the planet. These are some similar diagrams looking at different kinds of chondrites as compared to the Earth. And In fact, what I'm going to focus on is not so much the fractionation, like the hydrogen-carbon fractionation that I started out talking about, but rather simply the low concentration of carbon that we see in the bulk silicate Earth here or here. This one is too busy. Don't look at this one. Look at this one or this one. The very low concentration of carbon in the bulk silicate Earth as compared to the obvious cosmochemical sources, chondritic meteorites. There's very little carbon. And this is why the title of my talk is A Story of Loss. So this is work that I've done in collaboration with these characters over here. It's been a really wonderful adventure from my point of view. Some of you may know Jackie Lee. She's a mineral physicist, but the others are not really from the field of earth sciences. Fred Chesla is a planetary scientist. Ted Bergen and Jeff Blake are actually astronomers. And they have opened up my perspective on thinking about these processes, and such that the diagrams that I've shown you before, where I'm saying the building blocks are chondrites, they kind of laugh at that and say that I'm starting midway through the story and that I need to go, and that we need to go further back. The five of us published a paper in 2015, which is this little rectangle in the lower left there, tracing the ingredients for a habitable Earth from interstellar space through planet formation. So Ted and Jeff tend to look at things like protoplanetary disks, which one can see with radio telescopes, and to inventory quantitatively their chemical supply. And so they're able to provide to us things like the carbon concentration and the nitrogen concentration in these disks. And from their perspective, even when one talks about something like a carbonaceous chondrite, it's already lost a huge fraction of the available carbon, nitrogen, certainly hydrogen, also sulfur, as compared to what's out there in space. These elements are super abundant in space. They're more abundant than silicon and iron, for example, or magnesium as well. And the fact that the right amount, remember I said we ended up with the right amount. The Earth is way down here, orders of magnitude lower than these primitive materials. And the fact that the right amount is a tiny portion of what was available is kind of interesting to me. If we lost not 99%, but 99.99% to get to the right amount, that's a really interesting sort of set of circumstances. Fortunate for us, but maybe not so obvious how it happens. Last year, in 2021, this same group we continued working together and on the same problem. In this case, a pair of papers, one about the behavior of carbon in dust and the way it sublimates in early protoplanetary disks and how that affects the supply to planets. That's the paper that Jackie Lee led. That's on the bottom left, and I'm not really going to talk more about it. And then another, which was kind of an interesting excursion, as it were, was how to use iron meteorites to understand the process of carbon loss during planetary differentiation. And so I'm going to dive into iron meteorites, which I think some of you may know about, but I'm going to assume that are relatively unfamiliar to most of you. And first of all, describe to you why I think they're so interesting for this problem. And second of all, how we've been able to use them to talk about the problem of carbon loss. So when we talk about the processing of volatiles in planets and the loss of volatiles in planets, we can classify things in sort of three different environments. We can think about nebular processing, the things that happen basically to the unaggregated dust particles, and how that might vary radially in a protoplanetary disk in the solar system. We can talk about the planetesimal portion of it, and then we can talk about the planetary portion of it. And the planetary portion of it might be blowing away atmospheres by giant impacts or segregation of volatiles into the core. But it's the planetesimal portion of this that I'm going to emphasize. And again, I'm going to use iron meteorites to try to understand something about the planetesimal portion. When we have small bodies, kilometer to hundreds of kilometer diameter bodies, There's chemical processing that loses volatiles. How are we going to learn about that? Iron meteorites may not be the obvious place to look, but they are in fact an interesting place to look. These are actually not characteristic iron meteorites, but the carbon and the sulfur in them are quite photogenic because they have these big macroscopic segregations. Most of the iron meteorites that we're interested in don't have that. But indeed, iron meteorites have carbon, sulfur, measurable carbon and sulfur in them. Our collections of iron meteorites represent a large number of original parent bodies, possibly as many as 50. Rich Walker earlier this year told me that he thinks it's more than 100. So we have samples potentially of many candidate planetesimals from early in our solar system. Also, iron meteorites are amongst the oldest objects that we have in our solar system. When we determine when the iron meteorite parent bodies separated from the solar nebula, we get ages that are older than all of the chondrites. And the way to think about that is that any body that became appreciable size really early had a lot of aluminum-26 in it, and therefore it partially melted and differentiated. The chondrites, which did not partially melt and differentiate, did so because they were gathered up at some time later, when there wasn't as much aluminum-26, or alternatively, they're just veneers on bodies that were internally differentiated. The chondrites are the last dregs. The iron meteorites are actually the early stuff, and the early stuff matters. The early stuff matters because as we look at the evolution of photoplanetary disks, which we see here in the radio telescopes like ALMA and the Very Large Baseline radio telescope in the southwestern United States, we see that these disks evolve very, very rapidly within the first 500,000 years. And as they evolve, the amount of dust in these systems goes down by about an order of magnitude in the first 500,000 years. Where does that dust go? Well, it gets accreted onto its growing parent star, but it's also the material that gets into larger bodies like planetesimals, which no longer scatter. Another way to say that is most of the material that our planet and that terrestrial planets are made of were already in significant solids, big solids, in the first 500,000 years or so of solar system history. The iron meteorites are the place to look for that early material. The chondrites are the dregs. They're later. They may not be as relevant. This just sums up what I said. The observational record of early differentiation is in the iron meteorites. Oh, there we go. Iron meteorites are really interesting bodies. They are the cores, or at least the ones that we care about, the magmatic iron meteorites, are the cores of differentiated planetesimals. And what we actually sample for the iron meteorites are cumulates. They are the solids that precipitated from those liquid cores. And we can see fractional crystallization trends in them. And one of the great things about these fractional crystallization trends is that they depend very strongly on the sulfur concentration of the liquids. The trace element partition coefficients are strongly affected by the sulfur. And so this is, in fact, how people infer the sulfur concentrations of such liquids. And so we can get the sulfur concentrations of these cores based on their trace element systematics. The carbon, unfortunately, is not as easy. It's very heterogeneously distributed, even when it isn't so evident as it is in this micrograph here. And it's done, strangely enough, mostly before all of you were born, or almost all of you were born, by bulk analysis. These are the two papers from more than 50 years ago that gave us hundreds of analyses, of bulk analyses of carbon concentrations. And almost no work has been done since. But because this work was so comprehensive and so careful, it's still quite useful. I want to know the carbon concentration of these cores. But what I get in those analyses is the carbon concentration in the cumulates, right? So I need to reconstruct what the composition of the cores was. And this is I do with a thermodynamic model that looks at the carbon partitioning between molten iron alloy or iron sulfur or iron nickel sulfur alloy, actually, and the precipitated solid, taenite, which is the iron nickel liquidus phase that the cores are made from. And I will spare you the details of this, but let's just assert that given a set of conditions, I can calculate how much carbon was in the liquid from the carbon concentration of any particular solid. The results of that are in this plot in the upper right, or on the right rather. And each of these triangles represents a parent body of one of the iron meteorites. And the curves are the carbon concentrations that are observed in the solids. And the y-axis is the calculated carbon concentration in the parental liquid. And you'll see that the most carbon-rich ones have merely 1/10 of the weight % carbon, and they extend down as much as, or even more than 2 orders of magnitude below that. The cores of these planetesimals were already very carbon poor. And this is strange in part because carbon is siderophile. The cores will take as much carbon as they can from any silicate that they interact with. The fact that they have so little carbon really suggests that they were made from very carbon-rich bulk bodies meaning both the silicate and the metal. This is illustrated, same information illustrated in a different way, all the different iron meteorite parent bodies here. And there's kind of a busy graph, but just a few things. First of all, I've qualitatively put them into 3 groups: high carbon, medium carbon, and low carbon sulfur ratios. And I've compared them to the compositions of the chondrites themselves. And what we see is that most of the iron parent bodies, or their cores rather, first of all not first of all, it's true on both axes, have much lower carbon than those of chondrites. Why is this? The chondrites themselves show quite a variation, but it's very well constrained along a particular line. And that variation has to do with thermal maturation of chondrites and metamorphism of chondrites, which degas. And when they degas, they don't lose a lot of sulfur. They're nearly unchanged in sulfur. They may change a little bit, but they lose huge amounts of their carbon. But as they do, they stay along this trend, and the most processed ones are down over here. They don't reach down into where the iron parent bodies do, the cores. If we were to say, oh, let's just take all the metal from those chondrites and put them into the core, we would find that the carbon-sulfur ratio wouldn't change, but the carbon concentration would increase, and we would get bodies over here. It's not the right direction. It's not where the actual bodies are. So this closed system differentiation, or even if we allow melting to occur, but nothing else, just melting and movement of the carbon and sulfur into the metallic core, we would get compositions off in this direction, which we do not see and do not reproduce what we see in these cores. We can go further and make a model that incorporates not just segregation between silicate and molten alloy, but also degassing. We can measure experimentally, as we have, the propensity of these elements to go into the molten alloy. We can measure their volatilities in volcanic gas, their solubilities, if you were, in the silicate melt. And then think about melting not simply as internal differentiation, but also allowing degassing to occur. And that's what these kind of odd polygons are, with variable amounts from 0 to 90% degassing to an atmosphere overlying the planetesimal, starting from chondrite-like bodies of variable composition. And what we see is, so just to take this one, for example, this is 0 to 90% of a really thermally processed chondrite before it begins to melt. And it creates bodies, iron bodies, that are similar to this so-called medium carbon sulfur group, but not to the low carbon sulfur group. The low carbon sulfur group can only be reproduced in this environment if we allow comprehensive degassing of the body. If the body becomes completely molten with a magma ocean, and everything that forms in its atmosphere is then lost to space. And the effectiveness depends on the size of the body, meaning its gravity. So from a smaller body to a larger body, for different starting compositions from here to here and so forth. That's when we reproduce many of the parent bodies of the iron meteorites. Summary statement: the iron parent bodies record, not surprisingly, melting, but really profound volatile loss early in the solar system from planetesimals. This is a record of silicate degassing. The reason that I say that is if we simply imagined that we had a molten iron core sitting in space, we would find that sulfur was highly volatile, and we would find that carbon was not volatile at all, because carbon, in the absence of oxygen or hydrogen, has very low vapor pressure. Take an exposed piece of metal, the metallurgists care about this in a foundry, we would find that the partial pressure of sulfur would be 8 orders of magnitude higher than carbon. Such bodies would lose all of their sulfur and none of their carbon. The iron meteorite parent bodies, it's the opposite. They kept a significant amount of their sulfur, and they lost almost all of their carbon. This happens when one is degassing silicate, and the carbon can form volatile species like CH4 or CO or CO2, depending on the oxygen fugacity. And then suddenly carbon becomes very, very volatile. The severe depletion of carbon in iron meteorite parent bodies is the hallmark of silicate degassing. It's telling us what the whole body was doing, not just the iron. Carbon depletion in iron meteorites is the hallmark of processes in silicates. Okay, I'm nearly done. This is not the only process that happened, but when we think about the building up of planets, when we think about the material that may be thermally processed in the solar nebula, depending on whether conditions were far from the sun and cold, or close to the sun and hot, when we think about giant impacts and how they may degas planets, or core formation and how they may steal the life essential elements such as carbon or nitrogen, there's another dimension that hasn't received nearly as much attention, and that is the processing that happens on small bodies, on the planetesimal precursors. And at least for carbon, it seems that this was a really profound loss process. The differentiation of early formed, easily melted, and by easily melted, I mean they had a lot of aluminum-26 in them, planetesimals, lost orders of magnitude of carbon, likely, in the process. And the archive of this is, again, in kind of a surprising place in iron meteorites. So just to conclude, we don't really understand what the requirements of chemical habitability are, and it's not my field. I think some of you may know a lot more about it than I do, as to what the limits of what the limits of a supply might be to provide chemical habitability. But the process by which a planet gets to chemical habitability is not nearly as simple as this diagram. It isn't simply the location relative to the sun, colder, and too many volatiles far away from space, and you end up with an icy world, too close, and you end up with a mercury world. In between, you're just right. There's also several layers of processing that occur. And one of them, not the only one, but one of them is in planetesimals. And again, it's not very well studied, but it's a great adventure to be looking at meteorites and to be looking out in space at exoplanets and so forth, to be finding this evidence. And with that, I will conclude. Thank you very much.
Thank you very much, Marc. I'm going to stop the recording now.